Hello everyone, welcome to the week 7 of problem solving session for communication networks NPTL course. So today we will be first going through the basic concepts and then solving problem on layered architecture and dial-up subscriber line or DSL and slotted Aloha. So we will be covering the topics of Aloha, slotted Aloha, ADSL and layered architecture. So first we will go through the basic concepts of these topics and then we will go on to the assignments. We will try to solve them together. So with that, first we will tackle layered architecture. So layered architecture you can find in Behrus Farhausen Communication Networks book for your reference. So this is the book that I'm currently sharing in the screen. This is Communication Networks by Data Communication and Networks by Behrus Farhausen. So in that, chapter 2 is the layered architecture. So chapter 2 is layered architecture. So we will be covering mostly chapter 2 today. So the primary task of a data communication network is to send data from a transmitter to a receiver. So we have a sender or a transmitter and a receiver, and between them there is an intervening medium. So this medium can be air, this medium can be wire. So it can be either wire or wireless. So for here it is they're talking to each other. So the channel is wireless in the sense that the sound waves are traveling through air without the aid of any kind of connections. And now here we have no layers of communication. So whatever Maria is talking, Anne can hear directly. But if we want to if we want to have a more discrete communication where what Maria is saying is not decipherable to anyone except Anne. If we want such kind of a discrete communication, then we have to layer our communication rather than going to the normal through the normal route. So here whatever the Maria wants to say, she will first write it in a plain text, or she will talk, and then that will be encoded in a plain text. Now this plain text will be then put in an envelope, and then this envelope will be sent through the post office, and the receiver's post office will receive the envelope, and then the envelope will be delivered to Anne, who can open it and read the letter. So between Maria and Anne there is a communication at the plain text level. So they are communicating directly through plain text, but the plain texts itself are not accessible to anyone, any eavesdropper, if they want to attack the network. So yeah, so what I'm saying was that if Maria and Anne wants to talk with each other, they can talk directly through plain text, but that plain text will be encrypted in an envelope and sent via the US post. So the post office at Maria and the post office at Anne's place, they are communicating via the envelope. So they are communicating to each other via the envelope. They do not know the message. They are simply transporting the envelope. So this is one layer of communication, is when the envelopes are getting transmitted from one place to another. But above that there is another layer of communication where there is a cipher text. That is, the text is encoded into some kind of a cipher, and this cipher is not accessible to anyone who does not have the key to the cipher. So who has the key to the cipher? Maria and Anne have. So they can talk to each other. They can decrypt or encrypt this cipher to a plain text, and they can talk to each other in plain text. So this ciphertext level of communication is another layer, and the plain text level of communication is another layer. So this is a 3-layer protocol. Similarly, this kind of a protocol layering is also observed in data communication networks. So we will have physical layer. On top of that, we will have data link layer, then network layer, like that, 5 or 7 layers. So we will be going into the details of these layers shortly. So these protocol layers have two operating principles for protocol layering. That the first principle dictates that if you want to have a bidirectional communication, we need to make each layer so that it is able to perform two opposite tasks, one in each direction. So the for protocol layering, the both ways communication should be happening. So the layers should be able to transmit messages from both directions. That is, it should be full duplex. And the second principle we need to follow in protocol layering is that two objects under each layer at both sides should be identical. So the envelope that you are transmitting should be identical to the envelope you are receiving, and the letter you are transmitting at layer 3. So you are transmitting the envelope at layer 1, and you are transmitting the letter at layer 3. So the envelope at sender's layer 1 and the envelope at receiver's layer 1 should be same, whereas the letter at sender's layer 3 and the letter at receiver's layer 3 should be same. Now that so this is how protocol layering is done, and this is also followed in protocol layering is also followed in TCP/IP. So in TCP/IP there is a protocol suite. So the basically multiple protocols are stacked together, multiple layers are stacked together in a TCP/IP protocol. So a set of protocols. So TCP/IP means transmission control protocol / internet protocol. So this is a standard protocol set. So it has a 5-layer architecture. So the 5 layers are, these are the old 5 layers, you don't have to learn these. These are the new 5 layers that we will be following throughout the book. That is physical layer, data link layer, network layer, transport layer, and application layer. So when you want to send something, say an email to another person, so you are sending via gmail.com. So gmail.com serves as the application layer for doing the communication via email, because the Gmail is the application through which you are sending the email, whereas transport layer is responsible for the proper routing of the message from the sender to the receiver. Network layer is responsible for sending and receiving packets. Data link layer is responsible for sending and receiving frames, whereas physical layer means the actual connection that sends and receives bits. So physical layer is an actual connection that sends and receives bits, whereas so physical layer so here physical layer is an here physical layer is an here physical layer is an actual connection. Physical layer is an actual connection. So it is the actual connection of wires or wireless connection. So through this electrical signal, bits in the form of electrical signal, bits is transmitted. Now in layer 2, these bits are grouped together to form the bits are grouped together to form frame. So layer 2 sends frames. Then in layer 3 the frames are transformed to packets. In layer 4 the packets are transformed to datagrams. Datagram. And in layer 5 datagrams are converted to application specific data formats. So whatever data you're sending, video, audio, text, application specific, video, audio, text. So at the sender and receiver's application you should have the same video. At the sender and receiver's transport layer you should have the same datagram. At the sender and receiver data link layer you should have the same frame, and so on. So these are the 5 layers used in TCP IP protocol. Now here is a perfect example of how communication happens using these 3 layers, using these 5 layers. So in source A there is an application, say an email application. Let us consider email. So let us take an email application. So there is an email application, and using that you compose an email. Now this email is then sent to the transport layer, which makes datagrams. So datagram, and this datagram will be identical to the datagram in this transport layer. Next, network layer makes frames. Frames are made out of datagram is made out of frame. So frame is a more fundamental block. Now frames can be divided into packets. So it's packet, and then packets can be divided into bits. Now, so basically an email through multiple layers of encoding gets transformed into bits in the physical layer. Now these bits are transmitted from the wireless medium or wired medium through the medium. So this is the medium. It goes to a link. So it's a switch. So in this switch there is no application layer and no transport and network layer either. It just creates, it looks at the, it does a data link level to data link level communication. So like in the previous example, the post office did not need letter to letter communication. Post office only needed what was in the envelope. Post office just transmitted the envelope, so they didn't bother with what's inside. Similarly, what is the content of this email is immaterial for a switch. A switch is just a medium, so it will just try and take the data, take the bits, and from those bits it will try to decipher the next address, next hop, where it will go, and destination address. So based on the destination address it will give these switches have a tendency to forward it to the next. Based on the destination address it will forward to the next hop, next node. Now in the next node you again receive the bits, because they are again converted back to bits and transmitted via the medium. So these are again converted back to bits. Now these bits travel through the router, and again they get converted to frames. And in the router there is one change from the switch. While the switch just sends the data, the router routes the data. So if the data has a particular destination address, the router will have a corresponding next address, next hop. So according to the various destination address, it will have next hops. So whether it will go to this switch or this switch, link 2 to or link 3. So that is stored in the router. So based on the destination address, if the destination address is of C, then it will choose link 3. So here if destination is C, then link will be next hop. Next hop will be next hop will be 3. If the destination is B, next hop will be 2. So if C is through, this is the routing table of routing table. This is called the routing table. So based on the destination, it will route to the next hop. It will route the packet to the next hop. And once it is routed, then the packets are again converted back to bits and transmitted via the medium. Again there is a switch which will again give you the next hop based on the destination address, which is B. So it will just forward it to B. At B, you have received the bits. You decode it back to frames. So here you have bits. You decode it back to frames. Then you decode it back to packets. Then you encode it to datagram. And finally, you encode it into video or audio or whatever, text, whatever it is. So this completes the entire communication flow using a 5-layer networking device, 5-layer networking protocol. So the router has 3 layers as long as it is only used for routing, whereas the switch only has 2 layers, whereas the destination hosts will have all the layers, all the 5 layers. So the physical and data link connections are from switches to switches or devices to switch or switch to router, whereas the network layer connections are only through routers, and the transport layer and the application layer are directly connected from the source to the destination. It does not need any intermediary, no intermediary needed. So this kind of connection, so only the physical layer has a physical connection, others all have a fictitious connection or logical connection, no intermediary. Using logical connections, so this way, using logical connections, we can say that as if the application layer is communicating with another application layer, that is the user experience. So if you are sending an email, the receiver will receive the email in their own respective app. So basically from that app to your email app is the communication that is happening from your point of view. But beneath that email layer, the application layer, there are transport, network, data link, and physical layers that are working to send the message from sender to receiver. Now, sorry. Huh. So another way of thinking there is, now we will go into a brief description of each of the layers, starting from the physical layer. So the layers that we have talked about, out of them only physical layer is real. Physical layer is the only real layer that exists. Others are all abstract. They are all figments of imagination that we do to simplify the communication process. So physical layer is real. So what does physical layer do? Physical layer, let's jot down in a port. Uh, so here we have physical layer. Physical layer is at the bottom. So this is Physical layer is also called layer 1. So forms real wire. Then so it can be wired or it can be wireless. And what does it transport? It transports electrical signals in which bits are embedded. So it is so the bits received in a frame, the data link layer. So basically, what physical layer does is it receives the bits. So it receives the bits from frame of the data link layer. Then it modulates the bits and sends it through the transmission medium. So the logical unit between two physical layers in two devices is a bit. So we will take the bits, individual bits from the data link frame and modulate them according to according to some modulation technique, so that we can get valid electrical signals which we can actually transmit. Next we have data link layer. In data link layer we have seen that an internet is made up of several links. So there are multiple links. So a particular device might have multiple links. So one goes from Ethernet, another maybe goes to Wi-Fi. There is a dongle, so it is connected to Wi-Fi, and this is say LAN port. So there are multiple so there are multiple links that a particular data can travel through. So to resolve this link layer problem, which link it will travel through, we take the help of data link layer. In data link layer, the fundamental unit is called a frame. So TCP/IP, suppose the data link layer takes a datagram and encapsulates in a packet called frame. So it is called frame. So in this frame, there will be few information. So there will be like the destination address, host address, and some other bits, control bits are there, control bits, and finally data. So like that, from data, this is data. So from data, you encapsulate other informations and wrap it around the data to create frame. So now these frames will then be transmitted to physical layer, and the physical layer will break it down to bits. Next there is network layer. 1 minute. Sorry for the interruption. So now, as we were saying, now we will move on to network layer. The network layer is responsible for creating a connection between source computer to destination computer. It is also called a host to host layer. So if there is a host to host connection between two computers. uh, there are several routers. So between two computers. So if you have like the network layer, so in network layer, so data is capsulated into frames. Capsulated into frames. Then network layer creates host to host connection, that is between sender and receiver. It will create a direct connection between sender and receiver. So from a particular device you want to reach another device, so there may be more than one route available for that. So you go through one link, there is a router. Now it is connected to this link, and say there is another router through which it may be connected here. So there is one route that you can take. So one route you can take like this, route 1, or another route you can take like this. So this is route 2. So there may be multiple routes to reach the receiver device from the center device. To resolve the path, we need a host to host connection via the routers, and that is done by the network layer. So the network layer frames have the sender address, the receiver address, and the next address, all encapsulated in one frame along with the data and other stuff. So it will create a connection between sender and receiver via these routers. So the communication, we can say that the network layer is responsible for host to host communication and routing the packet through possible routes. So, and now you may say that what is the use for using so many layers? What is the necessity for using so many layers? So basically this network layer task can be relegated to the transport layer also, but the network layer is separated from the transport layer, so that at the routers we need only implement network layer. So we need not implement a transport layer or application layer in the router. So only implementing till network layer makes the implementation of the router cheaper. So in this sense, using a network layer is justified. Next, in the network layer, in the internet, there is this protocol called internet protocol, or IP. Now this IP defines the format of the packet. IP also defines format and structure of the addresses. So the, like I said, the sender and receiver address that you use in data link layer, the sender and receiver address you use in data link layer are hardware addresses, which are called MAC address. Whereas in network layer you use the network addresses, that are called IP address. So you might have seen that if you go to the terminal and write ipconfig, if you write ipconfig, you will see there is a local IP address. This IP address is 10.145.139.210. This is the network layer address. Whereas if you want to check the MAC address, you write here, you can see that you will have a for the wireless Wi-Fi adapter. Currently I am using Wi-Fi. So currently I am using Wi-Fi in this computer. So in this Wi-Fi you will see that the wireless LAN adapter has a particular physical address that is given as B0 70 64 87 D90. So this particular address is the physical address, and this will be used by the data link layer. And the IPv4 address, or the IP address, that is 10.145.139.210, this will be used in the network layer. So the data link layer, network layer will use IP address, whereas the data link layer will use physical address. Data link layer will use physical address, whereas network layer will use IP address. Now there are two kinds of IP address. One is IPv4 and another is IPv6. IPv4 will have 4 decimal separated integers. 4 decimal separated integers. So if you have this, for each 3-digit decimal, so the maximum you can go is 255.255.255.255. So this is the maximum you can go. So to represent each bit, each decimal separated integer, each integer, so you will need 7 bits. You will need 7 bits to represent all the integers, because 2 to the power 8 is 256. So 7 into 4, you need 28 bits. Here you need 28 bits. But in IPv6 there are 6 decimal separated integers. So here you have 6 decimal separated integers. So you will need 7 into 6 or 42 bits. So if we have IPv4, why do we go to IPv6? Because in IPv4 it was speculated that it will run out of addresses. how many addresses are possible in IPv4? In IPv4, 255 to the power 4 addresses were possible. While 255 to the power 4 is a pretty big number, the reality is that it's 4.2 billion. But the reality is that these 255 to the power 4 addresses are not used because of something called classful addressing. Classful addressing. The IPv4 addresses are separated into classes, and these hierarchical classes will limit the number of IP addresses that can actually be used. So that's why we do not have that many. We actually did not have that many IP address combinations as 255 to the power 4. We had less than that. But then network protocols moved on to classless addressing, and in classless addressing, basically that hierarchy was no longer followed. So we could have all the 2 to the power 28 or 4 point something billion addresses available. So that's why IPv4 still carries on, while IPv6 is used supplementarily. And mainly when people say IP address without mentioning anything, they say IPv4 address. Now, so IP is a connectionless protocol that provides no flow control, no error control, and no congestion control. So it does not provide any services to the data. It just provides the addresses, and you have to route through those addresses. Now this flow control, error control, these are all provided by the data link layer. So that's why these tasks are done at the lower layer. So these tasks are done at the flow control, error control, and these tasks are done at the lower layer. So this means that if any of these services is required for an application, the application should rely on the other layers to do this. Okay, so our routing protocol. So IP is a routing protocol. It will just route the addresses. It does not provide any kind of services like flow control or error control. Now transport layer is also end-to-end, and it creates a datagram out of the frame, and it creates a logical connection or imaginary connection between the source and the destination. It does not have an actual path through the router. It creates an end-to-end logical connection, does not go through routers, does not go through routers. Routers only have up to network layer, so it does not go through routers. Now, in other words, the transport layer is responsible for giving services to the application layer to get a message from an application program running on the source host and deliver it to the corresponding application program on the destination host. So in the TCP/IP protocol suite, this transport layer in TCP/IP provides a support to the application layer. In the OSI model, where there are 7 layers, actually there are other layers that support the application layer. But here, the transport layer only supports the application layer. So the transport layer will basically do this flow control and this congestion control, whereas error control is mostly done at the data link layer. So this transport will give the transport layer is independent of the application layer. So it will perform all these tasks like flow control and congestion control independent of the user application. So it will run beneath the user application, and this separation of tasks basically ensure that the application is not burdened with the networking aspects of the communication. So it creates a logical pipe between two TCPs for transferring a stream of bytes. So TCP creates this TCP or transmission control protocol. So this is the main protocol that governs the transport layer. TCP is the main protocol that governs the transport layer. So it creates a logical pipe, a logical connection between the two destinations, two end users, source and destination, for creating a byte, for transferring a bytes. So this provides, so this TCP provides flow control, that is matching the sending data rate and the receiving data rate. So the sender should send the data at a data rate that is manageable by the receiver. If the receiver is very slow and the sender sends the data in a very rapid manner, then the receiver won't be able to decode all the messages that are being transmitted. So at that time, TCP will step in and TCP will control the flow speed of the transmitter. It will reduce the flow speed of the transmitter. It will bottleneck the process so that there is an agreeable data rate flow which is decipherable to the receiver. And it also provides error control to some extent along with the data link layer, and congestion control to reduce the loss due to congestion in network. And another common protocol that is used in transport layer is UDP, or user datagram protocol. This is a connectionless protocol. So in in TCP, TCP was a connection protocol. So it creates a logical connection between the two devices, whereas two end devices, whereas UDP does not create any kind of logical connection. So obviously it cannot provide flow, error or congestion control. So UDP is a simple protocol and it cannot provide flow, error or congestion control. It just aids the transport of the data and does not have any kind of control. So it also has a small overhead. That means to implement it, you do not need that much resources. So the latency is less comparatively. So it has a small overhead. So it is attractive to application program that just needs to send short messages and cannot afford the retransmission of packets involved in TCP. So in TCP, if you have an erroneous packet, you again have to send the packet. So this kind of controls, that error control, flow control, and these other quality controls, they slow down the data communication. While the data communication will be more reliable, it will be more slow. So to write down the differences, so we have transport layer here. Now in transport layer, there is a source logical connection to the receiver. This is only true for TCP. For UDP, there is no such logical connection. So TCP and UDP, the differences are TCP creates logical connection, whereas UDP does not, is connectionless. UDP is connectionless. Now TCP has error, flow and congestion control. Do not have error, flow or congestion control. Next, in TCP you have a more expensive to implement. Expensive in terms of resources, so it will create more less latency, more expensive to implement, whereas UDP is cheap and has very low overhead. So depending on your kind of communication, you will choose TCP or UDP. If you have a communication need that only sends very short messages over a reliable channel, then you do not need error flow or logical control, congestion control. Then you can opt for UDP. But if you need a reliable communication, like video streaming or something, so if you need a reliable communication, then you have to switch to TCP. Because TCP, even though is more costly to implement, is more reliable. So next we will go move on to application layer. In application layer, the logical connection between two application layer is end to end. Again, it is an end to end layer. But this time we are sending the actual messages, not bits, not frames, nothing. We are sending the actual video message, audio message, whatever it is. So the actual video feed that currently is coming from my camera and reaching to your laptop, that actual video feed is communicated to the through the application layer. So my Google Meet and your Google Meet will kind of create a application layer to application layer connection. So this is where the actual communication that user experiences happen. And the few protocols that govern this application layer is HTTP, or which is a vehicle for accessing www, so or World Wide Web. So HTTP is a protocol that governs this all the websites. So that's why you will see most of the time in all websites you will have HTTP or HTTPS. And then there is SMTP, which is used for email services, and FTP, which is used for file transfer services, and SSH, which is used for accessing device remotely. Now what happens is in encapsulation and decapsulation is the key essence of protocol layering. So at every stage, the message from the application layer, it goes down via the TCP layers, and at every stage some part is added to that message. So nothing is removed from the message, only addition happens. So this at the from application it goes to transport, and a header is added, and this becomes a datagram. So this becomes a, when message you add a header, you add the transport layer header, you get the datagram. So it goes like this. At top you have application layer. Here what do you have? You have message. Now at the transport layer, you will have message plus a header that is obtained from transport layer. So TH is the transport header. So this is the datagram. which datagram which is equal to message plus transport header. So we have encapsulated the message with a transport header. Now it goes to network layer. Here, this datagram, that is message and th, message th, this datagram is added with a dh or nh or network header. So this is called a packet, IP packet. So packet is equal to datagram plus network header. So datagram is message plus transport header, whereas packet is datagram plus network header. Network header. Now you go another layer down, and you have oh, is my screen not visible? I was sharing the screen. Oh, anyways, it has stopped probably. I'm sorry. Please, if you have any other problem, you may unmute yourself and you may ask at any time. Okay, this is an interactive session. So, yeah, I think, yeah. So sorry for that inconvenience. Yeah. Now, from network, you go to data link. If you have missed the screen recording of the this part, so I will be recording this in the NPTL course page. You will see a live problem session tab. In that live problem session tab, you will get the recording for today's. It will be up by today night only. So in that you will get the recording of today's lecture. In that you can see the entire screen in the recording. So this, if you have missed the live recording, kindly consult that video. You will get the entire screen. Okay. Okay. So from here, now this, here we have the datagram. Now the date from packet. Now datagram is converted to packet. Now another header is added, which is the data link header, DLH. So this DLH is added along with NH and TH and the message. So this is called a frame. So what is a frame? A frame is a datagram, a packet plus data link header, DL header. And finally, this entire thing is then transformed to bits in the physical layer. This is entire thing is transformed to bits string, like 00110110. So this encapsulation goes on till data link layer. After that, in physical layer there is no encapsulation. So after that, these bits are this frame is converted to bits in the physical layer, and then they are modulated. Of course, you cannot send bits over a channel, so they are modulated according to some modulation scheme. And then they are transmitted, and then this along the transmission it will go, and then it will reach the router. At the router there is a physical layer. This, what will this physical layer do? This physical layer will create frame, like decode bits. So this physical layer has encoded the bits to symbols. Now this physical layer will decode them into bits again, and then those bits will be encapsulated into a frame, and then that frame, those bits will be rather formed into a frame, and then from the frame we will remove the data link header, and when we remove the data link header we get the packet. Because here you can see frame is equal to packet plus data link header. So when you remove the data link header from the frame, you get the packet. So you will get the packet. This is the packet, and this packet has the source and destination address, IP. These are the IP address, of source and receiver. Source and RX. So from there it will see the destination address, and from the destination address it has a local routing table. Based on the destination address it will create the local. Based on the destination address it will create the local, and then from there we will go to from the it will get the local address, and from the local address then again we will follow the encapsulation. So here we had encapsulation. So you were quoting the message in a capsule, and then here we had decapsulation, of course. Then at the router again there will be another round of encapsulation. Here we had decapsulation, here again we will have encapsulation, like that. So then this again we will encapsulate, and then we will convert into bits, and then bits into symbols, and then we will transmit to the destination. At the destination again another round of decapsulation will happen. The bits will be formed into frames to packets to datagram to message. So like that one round of communication will happen. So this is encapsulation and decapsulation. Now addressing in TCP/IP, at the application layer, the addresses are basically the sites, websites, so or emails. So somebody at hotmail.com or somebody.com. So these are the addresses at the application layer, and these addresses are then coded into transport layer. So coded into port numbers at the transport layer, and from these port numbers at the network layer we get the global addresses. These global addresses, basically port numbers, are local addresses that distinguish between several programs running at the same time. And once we have done that, then you come at the network layer where you will have global IP addresses. These are the IP addresses, and then you have the data link layer where you have the hardware MAC addresses, and from that MAC address you can exactly isolate a particular device to which you will be sending. Now we come at a rival model for TCP/IP called the OSI model. The OSI model is having 7 layers. The first 4 layers, physical, data link, network and transport, are common for both. But in the OSI layer, the application layer is divided into 3 parts: session, presentation and application. So there are multiple application protocols in one application layer in TCP/IP, whereas those are neatly divided into 3 layers for the OSI. The bottom 4 layers for TCP/IP and OSI are same. So in the end, this OSI layer was suggested as a rival to this TCP/IP layer, a TCP/IP protocol model. But OSI model never properly fully replaced TCP/IP because the first 4 layers are same, and the presentation and session layer protocols are not properly defined. So at the end of the day, we stick to TCP/IP model. but there is another rival model, so you should know about 7-layer model. And the main crux is that the first 4 layers are same, and the application layer is further divided into session, presentation, and application. But some layers of the OSI model were never fully defined. For example, although the services provided by presentation and session layers were listed in the document, actual protocols for these 2 layers were not fully defined, nor were they fully described, and the corresponding software was not fully developed. So the Internet Authority did not switch to TCP OSI model from the TCP/IP protocol. So even today, TCP/IP protocol is only followed, the 5-layer protocol. So from this, we come to the end of the chapter for protocol layering, and with that, I think it is time enough to let's go to the problems. Let's go to the problems. Since this is a theoretical chapter, today the problems will be more will be more of a theoretical kind. So we'll see. It's not that much of a problem as it is in different like previous lectures. So state whether true or false in the TCP/IP net stack network access layer is equivalent to transport in the OSI model. So as I said, the only difference between TCP/IP and OSI stack is in the application layer. The first 4 layers, physical, data link, network, and transport, are same. So the network layer of TCP/IP is not equivalent to the transport layer of OSI model. It is equivalent to the network layer of OSI model. So the network layer of TCP is not equivalent to network layer of OSI. So here the answer is false. So it is false. So this is equivalent to the transport layer. Now Now, which layer is of TCP/IP is equivalent to network layer of OSI? So, like I have said, TCP/IP and OSI are same for physical, data link, network, and transport layer. They only become different at the top layer, application layer. So that's why the TCP/IP model network layer is equivalent to OSI model network layer. So network access. Okay, network access is also sometimes called internet layer. So I think they have said internet layer here. So internet layer is also equally true. Network access layer is also equally true. So I think both C and D, here it is written as C. So state whether true or false. TCP/IP models application layer only maps to application layer of OSI model. So here lies the difference that in TCP/IP there is an application layer in TCP/IP. This is equivalent to 3 layers in OSI: application, session, and presentation. So here, true or false, TCP/IP model's application layer only maps to application layer of OSI model, which is not true. It maps to 3 layers. So it is false. State whether true or false. Internet layer is responsible for routing operation in TCP/IP model. So this is again, internet layer is mainly responsible for routing. So it is true. Of course, the main purpose of internet layer is to route the packets. So how does it route? It routes IP of host to IP of destination via routers. This is router. Via router, it will go to IP of destination. So this is the main task of internet layer, or you can write network layer here. You can write network layer. They are the same thing. So it is true. Now, which layer is responsible for ensuring packet delivery from host to destination? So from host to destination, who will ensure the packet delivery? So the packet delivery, the main task the answer lies in the word transport. The main task of the transport layer is to transport the packets from host to destination. So it will be the transport layer. Okay. Now, with this, we have come back to the end of questions regarding protocol layers. Now, we will go to the ADSL system. We will go to the next topic today, ADSL system. Okay, not here. Mm, mm. So, yeah, yeah. So now we will move on to some network called digital subscriber line. So previously, before these LAN cables and routers were ubiquitous in homes, internet used to come through telephone system. So there was a telephone office. From that office there was a trunk line. That trunk line came to the small exchanges that were located across the locality. Even now you can see at various localities, even now you can see there are BSNL exchanges. So from regional office, the regional the connection goes to the exchanges, and from exchanges the connection was distributed to homes via local loop lines. So local loop line is basically normal cables that are connected from your landline to the exchange, telephone, nearby telephone exchange. And trunk is basically a common line that is has multiple channels and that handles all the devices that are connected in a particular exchange. So then from there it goes to a switching office, and from there regional offices. So this was how commonly internet was accessed before Ethernet and Wi-Fi were ubiquitous. So we will directly go to, instead of using this, we will directly go to dial-up services. So in dial-up services, traditional telephone lines used to carry frequencies between 300 and 3300 hertz, giving them a bandwidth of 3 kilohertz. It is good for voice, but it was very slow for data. So the effective bandwidth was only 2.4 hertz. It was 2.4 kilohertz. So we had a very slow data connection in those times. So dial-up service had a very slow connection. Now we used to have modems, and this modem stands for modulator demodulator. These modems used to have take the telephone line, occupy the telephone line to transmit its signals. And when you were using the dial-up internet, you could not use the telephone at the same time. That's why. Now, so after these traditional modems were used, then telephone companies developed another technology which is called DSL, or digital subscriber line. So digital subscriber line has multiple implementations: ADSL, VDSL, HDSL. So if we will discuss the first technology, that is called ADSL, or asymmetric DSL. Okay, asymmetric DSL provides a higher data speed in the downstream than in the upstream. That is, from the internet to device, the speed is faster, which is mostly what is needed, download speed. So yes, basically what happens is the bandwidth is divided equally. If you do nothing, then the bandwidth is equally divided between the upstream and downstream. In ADSL, downstream was prioritized and it was given a higher bandwidth. And that ADSL used to use the existing local loop, existing telephone lines only. But how does an ADSL reach a data rate that was never achieved with traditional model? The answer is that the twisted pair cable used in telephone line is actually capable of handling bandwidth up to 1.1 megahertz. But the filter installed at the end office of the telephone company, where each local loop terminates, that is at the exchange, limits the bandwidth to 4 kilohertz. So even though the twisted pair cable you had 1.1 megahertz bandwidth, you only used 4 kilohertz of that bandwidth, because that is good enough for voice communication. When that filter was removed, the entire 1.1 megahertz was available for communication. So what happens is, you have a splitter. So you have a landline and ADSL modem, both connected to a local loop line. That local loop line will connect to the regional exchange, and from that regional exchange, the voice landline, so basically the landline communication, the voice communication, will go to the telephone network from the local exchange, whereas the data will be split, and the modem requirement, the modem, whatever the modem data is, that will be transmitted to the router through the internet. So basically you are taking in both data, mixing them, and then you are separating them again at the exchange, so that the internet packets go to the internet and the voice packet goes to the telephone. So in this is how digital, so we use at the exchange, we used a digital subscriber line access multiplexer, or DSLAM. So this DSLAM, what happens is, it enables us to separate voice and data, so it can separate the voice and data channels. And once the voice and data channels are separated, then you can of course transmit both together. So we can now communicate and send data together. And you can see the downstream bandwidth is much more than the upstream bandwidth. This gives the name ADSL, asymmetric digital subscriber line. So see, we have 1100 kilohertz bandwidth. Out of that, 1000 kilohertz is used for downstream communication. Nearly 100 kilohertz is used for upstream communication, and only 4 kilohertz, the remaining 4 kilohertz, is used for voice communication. So that's how you divide the entire 1.1 kilohertz. This is called the ADSL. Now we will go to some remaining problems. Let there be a noiseless 8 kilohertz channel. What is the maximum data rate? So, if there is a noiseless channel, what is the maximum data rate? The data rate is limited by the Shannon's equation as C equal to B log 1 plus SNR. This is called the famous Shannon's equation. Okay, Shannon's equation. Where C is the capacity or max data rate. C is called capacity, and this maximum data rate also means capacity. So this means capacity. So if it is noiseless, so SNR is signal by noise. Noiseless means noise is 0, so S by 0, so this is infinity. So what does log go to? As infinity, you approach infinity, so log goes to infinity, so this will again be infinity, this will tend to infinity. So you have unlimited capacity. So if you do not have any noise, you do not have any restriction to send data, you can send as much data as you want, but that is not possible in real life because you have noise. Okay, now time required to v.32 bits. Now v.32 using v.32 bits. So 1 minute, let's go back here. So v.32 bits here. v.32 bits is a standard. Okay, it is a standard for ASDL, asynchronous digital subscriber. So this is now this is what is called the, here in this book it is called the 56K modem. Let me go to where this v.32 bits. One second. So this 56K modem, this is called the v.32 bits. This follows the v.32 bits standard of ITU. This is a particular standard number of ITU. Standard of ITU, International Telecommunication Union. Okay, so now here the data rate is 56 kbps. That is how it is limited. So yeah, traditional modems have a data rate limitation of 33 kbps determined by the Shannon capacity. However, modern modems with a bit rate of 56,000 bits per second are available. These are called 56K modems. These modems may be used only one party is using digital signaling. They are asymmetric in that the downloading rate is maximum of 56 kbps while uploading can be maximum 33. So this is a kind of modem which you can get 56K kbps maximum speed. So particular standard. So what is the time required to download 1 MB or 1 million bytes? So 1 MB means data is 10 to the power 6 bytes. 1 million byte 10 to the power 6. So time required is thus data by data rate. Data by data rate. Now data rate is 56,000 bits per second. Okay, you have to mind that. This is bits per second. But this is 1 million bytes. This means 8 million bits, right? So the actual data rate is 18 to 10 to the power 6. So this is 10 to the power 3 by 7 bits. So 10 to the power 3 by 7 seconds or 142.8 second. 142.8. So correct answer is option A. So here just the trick is that the data rate is 56 kbps. kbps. That's it, nothing else. Now you just divide. Data rate is 56 kbps. Here b is bits, not bytes. Data rate is 56 kbps. That's why it is a small b. If it were a byte, then you would have written like this, kbps. Okay. Usually bits are used in networking, not bytes. Now, an ASDL using DMT allocates half of the available data channel. DMT is some protocol to allocate channels. Allocates half of the available data channel to the downstream link. It uses QAM32 modulation on each channel. What is the capacity of the downstream link? So there are here there are 256 channels total. 256 channels total. Now this you have to see for the particular standard what are the number of channels, how many are reserved for voice, how many for control. So out of that only 248 are available for data. 248 available for data transmission. Available for data transmission. Right? Now half is for downstream. So how many channels available? 124 channels for downstream. Now what is the yeah. Now QAM32 encoding has 5 bits per symbol because it is 32, 2 to the power 5. So 5 bits per symbol. And DSL is 4000 symbols per second. So the calculation is that for how many, what is the bit rate? So if DSL transmits 4000 symbols per second, so you have 20,000 bits per second per channel. So now for every channel, if you transmit QAM, you have 5 bits per symbol and 4000 symbols per second is the baud rate or symbol rate. So each channel has a 20,000 bits or 20 kbps capacity. So if you use 124 channels for download, you will have a maximum speed of 124 into 20 kbps or 2.4 mbps speed, 2.48. So the correct answer is none of the above. Now, a full duplex QAM64 modem uses separate frequencies for upstream and downstream. So since this is a frequency domain full duplex, that means that if what is full duplex? Full duplex means if you have a transmitter and you have a receiver, that like device A and device B, A can communicate to B at the same time B can communicate to A simultaneously. So if they can do it simultaneously, that means A and B must be differentiated somewhere. They can be differentiated in time, that is A sends then B sends, but that is not the case. We are saying they are transmitting simultaneously. So what differentiates this communication, A to B and B to B? A to B uses a particular frequency F1, B to A uses a particular frequency F2. They have to use different frequencies. Somewhere they have to differentiate themselves, or else there will be interference. So a full duplex uses separate frequencies. And then how much is the maximum bit rate achievable in a V.32 modem if the rate is 4800 symbol per second and no error correction is used? So if there are no error correction, so 4 bits per symbol will be used. If V.32 means 56k modem. So look into the 56k modem in Farhausen book and you will see that it uses 4 bits per symbol. Assuming it uses 16 QAM. Unless otherwise, you can assume it uses 16 QAM default. So 4 bits per second and rate of symbol is 4800. So you multiply that you get something like 192 bps, so 19.2 kbps. So the correct answer will be 19.2 kbps. Now the values for this bit means bit rates or symbol rates that you have to check with the correct standard. So v.32 has a particular value for bits per symbol or symbol rate. So not all the data will be given. If they specify a particular standard, then in the exam not all the data that you need to solve the problem will be given. Some of the data are standard, so you have to know the standard by heart and you have to recall the value, like 4 bits per symbol will be used. It is nowhere given that 4 bits per symbol will be used, but because they are specifying the standard v.32 standard, that means that 4 bits per symbol is used unless otherwise specified. In one problem you will see that there was 32 QAM. There was probably 32 QAM if I'm not wrong. Let's see. Yeah, QAM 32 modulation. See here there is QAM 32 modulation. So of course bits per symbol will be 5. But if nothing is said, then you have to assume the standard values for this particular standard. So v.32 standard has a particular standard value of 56. Of 4 bits per symbol, and the maximum download speed will be 56k kbps. That's why it's also called a 56k model. So this is v.32. Now with this we come to the end of this class. That we have solved the problems. The solved problems will be uploaded to the problem solving tab in NPTEL. And for now I will be happy to take any questions. Is there any question? Is there any question?
No sir, no sir.
Okay. Then your video will be uploaded by tonight and also the solved assignment. So you can go through that, and please join back again next Tuesday 6 o'clock. Thank you.
Thank you sir.